What's up, everybody? Welcome to my basement for a little stat session. Sorry I can't be there this week. I hope you guys are using your time productively. We will have a test coming up on Tuesday, and you're responsible for all the stuff you're supposed to be learning. So I'm hoping that you're making the right decisions, and if not, you're gonna turn it around and start doing that today, and make up anything that you have not completed throughout the week. Some of that con stuff, Google Form exit slips. We're gonna have another exit slip today, but I'll shut up. So let's jump into our new stuff. We're gonna take some notes. So you should have your notebook out, write some things down. After this, you're gonna have a Google Form assignment based on these. Tomorrow you'll have some additional practice based on what we discussed today. So here we go. I'm having a little tablet difficulty, so writing on the screen's a pain, but so bear with me when it gets sloppy. So today we want to talk about inferences about populations, or in other words, the conclusions that we can draw about populations from a sample. That's kind of the whole reason we're doing all this, and we'll talk more about that when I'm back. But really, the reason we've been studying stats and what makes stats powerful is we can use sample data and draw accurate conclusions about a population. But it's not just as simple as what we've done so far. So let's get into it. So suppose you take a random sample of 75 trees in East Hartford. Using some trig ratios, we'll learn how to do that in the spring. To calculate the heights of 75 trees, we find an average height of 54 feet. Now, let's say here our goal is to find the average height of all trees in East Hartford, but I don't have time to measure the heights of all the trees, so I just want to use a random sample. However, I have some friends' help, and my friends here, these legendary 2022 Giants players, they also take random samples of 75 trees, and they find their own heights. And so my friend Saquon gets a height of 56.2, Daniel Jones gets a height of 58.1.8, Xavier McKinney 52.5, Darius Slayton 55.5, and Leonard Williams 54 feet. And the question is, right, remember we had an average for our sample of 75 trees of 54 feet. And the question is, which of these five would you be most surprised by? Are you most surprised when your friend Saquon's like, yo, my average was 56.2? Or one of the others? And now's an opportunity to pause this video, turn to the person you're sitting next to, and have a conversation. Which one's most surprising to you? And now you've unpaused. And so I might get some people who say they're surprised by the 56 and the 55 because they're higher. Or maybe I get some people who say they're surprised by the 51, 52 because they're lower. But really, 56.2 is 2.2 feet above 54, and this is 2.2 feet below. So they're like the same distance above and below. I did that on purpose. So I can't really argue one's more surprising than another. And I did the same thing here. This is 1.5 feet below 54, and this is 1.5 feet above 54. So I can't really argue either of those one of those is more surprising than the other. And hopefully some of us in the room, we're kind of thinking, this is the most surprising, because if my friends took random samples of 75 trees, we all have different random groups of trees. It would be kind of crazy if the average that I got and the average that my friend got using two totally separate groups of 75 random trees. We might have one or two trees that we chose the same that overlap, but our groups of 75 are both random and different. It would be kind of wild if we got the same average. So hopefully, at least one of us was thinking about that and maybe even shared it out loud. So really, that's what's the most surprising. We are not surprised when we keep taking samples and getting different statistics. If I stopped 5 people in the hallway and got their average GPA today, and then tomorrow I stop another 5 people in the hallway and find their average GPA, I don't expect to get the same number. That would be kind of crazy. It's 5 different people that I'm not really randomly choosing. That's a convenient sample. Hopefully you do that too. So this is an idea that we call sampling variability. And this is the first thing we want to put in our notes. Sampling variability is just the idea that sample statistics vary from sample to sample. Or in other words, what we're saying here, sample statistics, measures of center and spread vary, or in other words, differ from sample to sample for each random sample. So what I'm writing in black is just another way to say what we see in blue. That's what we're seeing in the table. Saquon takes a sample of 75 trees, gets his average. Daniel Jones does the same thing, gets his average. These are different. That's not surprising to us. Now, what we have to start to think about eventually, and this is what we dive into in AP stats, where I'll see some of you, is how different would be surprising. We'll save that conversation for another day. We'll also save this for another day, but this is a link I'll post where you can kind of play with the idea of taking random samples and seeing what happens. So I'll link that in the class. So that leads us to the next question. Oh, no, it doesn't yet. This is just another picture depicting sampling variability. Maybe I got a bag of marbles. I take out a handful of 10. Maybe the first time my handful has 5 green and 5 yellow. When I take out my next handful of marbles, I don't expect it to be the exact same as the first. I don't expect it to be exactly 5 and 5 again. Maybe this time I get 6 yellow, 4 green. And then same thing, when I take another random sample, another handful of marbles, I don't expect it to be the same as the first or second, right? I get 7 yellow, 3 green. That doesn't surprise me. The idea that the handful looks different every time, that's sampling variability, and that's not surprising. So that leads us to the next question. And this is a good one to pause and talk to your neighbors to as well. Our goal is to estimate the mean, in this case, the mean height of all trees, the average height of all trees in East Hartford. And so the question is, you can see now we've added us to our data. If these averages, if every time we take an average, we get a different number, how can we possibly find or estimate the average height of all trees in East Hartford? I can't just use any one of these numbers because there's no reason to think any one is better than another. So now we're just looking for ideas. So this is another one of those opportunities. Pause the video, turn to your neighbors, and just start bouncing some ideas around. That's what I would ask you to do in class. And don't worry about if it's right or wrong, right? Just try to think, what might I do? Pause the video. Really do that. Right. Pause the video. So here's the deal. Here is the next piece of notes. You might even write all of the stuff on the screen down. This might be a good opportunity to pause, kind of write everything you see, and then unpause and really look at what we're doing and kind of color code along with me rather than just trying to copy and not listen. So I would recommend pausing, really write this down. The whole table would be useful, and this will help us understand what's going on. So here's the deal. In order for us to estimate the population mean, the average height of all trees in East Hartford, we're going to use what's called a confidence interval. We cannot pick any one of these numbers and just say, oh, the average of all the trees in East Hartford is 56.2 or 55.5, because we know every time we take a sample, we expect to get a different average. So what we're going to do is we're going to give an interval estimate. We're going to say, you know what, we think the average height of all the trees in East Hartford is between 51.8 and 56.2 feet. I might have said it just before, that'd be a small tree. And usually we're going to associate that with some confidence level. We're not going to say we think, we're going to say something like we're 95% confident or 98% confident or 99. The construction of these confidence intervals is something, again, we dive deeper into in AP stats. And if you notice here, right, this is using the 51.8 we have and the 56.2, which happen to be for this data the highest and lowest values. So that's what we're looking at all these numbers. We're like, hey, you know what? The average has got to be somewhere between, well, not got to be, we're pretty sure, 95% confident. The average is between 51.8 and 56.2. So there's some other things to break down here. The middle of this interval, the number right in the middle of this is going to be 54. And that's not a coincidence. That's the sample mean that we started with. And then we're going to add what we call a margin of error. The margin of error is the amount we're adding and subtracting on either side of our sample mean or percentage to get the interval. So I start with my sample mean, which is 54. From there, I'm going to add or subtract this margin of error of 2.2. And if I do that, when I do 54 plus 2.2, that's how I get this 56.2 number. And when I do 54 minus 2.2, that's how I get this 51.8 number. And so in a lot of instances, what we started to see in our Delta Math assignment I gave you guys the other day is that we're going to be given the mean and the margin of error, and we're going to have to use those numbers to create this interval, right, which is based on this work. If we get more advanced, I might give you just this interval to 51.8, 56.2, and ask you to work backwards to give me the margin of error and sample mean. Quite honestly, those are AP multiple choice questions and AP stat. So this is really laying the foundation for a lot of things we dive deeper into in the second semester of AP stat. But anyways, I'm just trying to recruit a lot of you. So that's the idea, right? If we want to estimate a population mean, we start with the sample mean. We can't just use the sample mean because sampling variability. So we take the sample mean, we add or subtract margin of error, and that gives us this interval estimate for the population mean or percentage, right? That's the general idea. We're not going to have to learn how to calculate margin of error in this class. It's going to be given to us. What we need to know is what's on this screen. So really, the end of your notes, because then we're just going to look at a couple examples. Same thing. I would pause the video. I would kind of write all this down and then hit play, kind of listen to what's going on. So the margin of error, that's the amount we add or subtract on either side. Whoops, of our statistic, right? So if I start with 54 plus or minus 2.2, this 2.2, the amount that we're adding and subtracting on either side, right? That's my margin of error. Why didn't I use purple? And then there's a few things we have to know. As you'll see this show up in a couple questions, and you're about to do 5 in a Google form about this. So 1, margin of error is used to estimate the mean or percentage of a population. So margin of error is not used to talk about the sample. We have the sample data. We don't need an interval for the sample. So we have to think about what's the population that we're trying to represent. And that's some of the key wording we'll look for in the multiple choice. That must be really important because that's literally the same thing that number 2 is. Margin of error is about the population, not the sample. So from looking at lots of SAT multiple choice, that's oftentimes a key distinction between a couple of the options. The last thing we need to know is how we can decrease margin of error. And if you think about it, pause the video for a second. It has to do with the data we collect. How could we get a more precise estimate? Think about that. And honestly, now that you've unpaused and stopped thinking about it and discussed with your neighbor, it's not really that surprising of an answer. If we get more data, which I'm writing horribly with my mouse, or in other words, if we increase the sample size, we're going to decrease the margin of error. Because what that means is if we're going to increase the sample size, we're going to get a more precise estimate of a population parameter, or of a population mean or percentage, I should say. We'll talk about the word parameter Monday. And again, that should not be surprising to us. More data means smaller error. So this is not something that came up in the math we discussed, but that is something that we absolutely, right, have to know and remember. You'll see that in, I think, the second multiple choice. So remember, smaller margin of error, bigger sample size. Write it down. All right, so here's what questions look like. So check it out. Scientists conducting an experiment to see if soybeans grow differently in traditional greenhouse versus growing in a zero gravity environment. Study estimates that the average height of soybeans grown at zero gravity is 30 centimeters with a margin of error of 8. So let's kind of summarize what's going on before we even look at the multiple choice options. So the sample is the soybeans in the experiment. The sample, we know that the mean is 30. We do not use margin of error to draw conclusions about a sample. I know the exact mean for the sample. I don't need any kind of confidence interval or margin of error for that. So the confidence interval and margin of error are for our population. So our population would be all the soybeans, not in the world, but the ones that are grown in zero gravity. And from here, we can't just say the mean is 30. We have a sample mean of 30 and a margin of error of 8. So our confidence interval is going to be 30 plus or minus 8. Whoops, 30 plus or minus 8, or in other words, 22 to 38. And what that means is we think the mean height of all soybeans in zero gravity is between those two values, between 22 and 38 centimeters. Right, so that just kind of recaps everything that's going on. Now, the one thing I want to point out is I capitalized the word mean because I know in some of the practice we're going to see that, or we're going to see right here, right? Like this is not talking about the average height. So this is tricky, right? The reason A is not the answer, it has the right interval, right? It's got the correct values, but it's not talking about the average height. So A is out. This word is critical. A confidence interval, we use margin of error to talk about means or percents of samples, right? Remember, that was the first thing we wrote down here. It's got to be about a mean or a percentage. So A's out, B's out for the same reason. Also doesn't use the interval, but tries to talk about the population. So that leads us to C or D. We're talking all soybeans in the zero gravity or soybeans in the experiment. So C's got the sample, D's got the population. Both are using the interval, but an interval is used for a population. They both have the word average. So the distinction here is in this chunk. C is talking about average and uses the interval. D is talking about average and uses the interval. But the interval should be used for the population, which is D, not C. The interval is not used for the sample because for the sample, we have the mean right there. And that's a pretty typical type question you're going to see. So let's jump to the next one, the last one, right? That's exit slip time. So factory produces only one type of product. Estimate the mean weight of the product produced by the factory on a particular day. That means this is the wording that we're going to have to use in our multiple choice response. But so we want to estimate the mean weight of the product produced by the factory on a particular day. They took a sample of the product produced that day at random and found the mean weight in the sample was 19.8 ounces, and they gave us a margin of error of 0.2 based on the sample mean and margin of error, which is the most appropriate conclusion. Pause the video and see what you think. We see the same distinct thing we saw in the last question. We're not talking about actual weights. So these are out, right? We're talking about mean weights and mean weights. But again, when we're talking about all products that are at the factory, that's our population right here. A population, we don't use the sample number because sampling variability, we need to use the interval. So again, we're going to choose D. So your job right now is to complete a Google form, but this is a little bit different. This is based on both effort and accuracy. The first thing you're going to do is you're going to complete the Google form. It's 5 questions. What you're going to do then, all right, is use your notes, do the best you can. Hopefully you get a perfect score. When you're done, you're going to see what you got wrong. It's not going to show you the right answer, but it's going to show you some feedback. It's going to explain how to approach the question, which if you read will give you, you'll figure out the right answer. And what you can do is you can do the Google form again. So your job right now, right, the first thing you're going to do is you're going to do the Google form. Then the second thing you're going to do is you're going to look at how you did. You're going to look at the score. But more importantly than that, you're going to read the feedback that is provided, right? So it's going to tell you, you'll see boxes, right? That kind of explain the question. After you read that feedback, you're going to try to identify the correct answers, because then what you can do is you can redo the form and I will only count the higher score. That means every person who puts in max effort gets a 100. If you don't, you just chose not to earn a 100. Right? You got to take the time, try your best, learn from your mistakes, just like we build our understanding from the answer key, and then, right, do it right the second time. Tomorrow's classwork, we'll have a short video. Then it's going to have another Google form that'll have some of the new stuff, but it will also have some of this margin of error stuff again, I think. All right. So go ace that. Have a great class, and I will see you guys Monday. Oh, by the way, Lincoln has the flu, and I'm out all week. I totally meant to say that in the beginning.